Our next speaker is Glassman of WSP Built Ecology. Elliot has worked on a wide range of project types in the U.S. and abroad, including multifamily residential, mixed-use buildings, commercial, religious, institutional, government, and hospitality. He is currently working as a building performance consultant for WSP Built Ecology here in New York City, helping fellow architects meet the sustainability goals of their projects. His work incorporates a variety of performance simulation tools with parametric models to arrive at more environmentally responsive and optimized designs.
Thank you very much. Hi everyone, I'm Elliot, and as mentioned, I'm an architect with the New York office of WSP Built Ecology. It's one of 6 offices that we have worldwide. It started off in Australia, so we have offices in Melbourne, Sydney, and Brisbane, and then expanded to North America with the San Francisco office, and then in 2011 to New York and Boston. I joined the team in 2011, last year. And welcome to my talk titled Data-Driven Design, DIVA and Grasshopper Studies for Climate Responsive Evaluation and Optimization. The central theme of my talk is going to be that using Rhino and Grasshopper with DIVA could be a pretty useful tool for us to create high-performing designs informed by simulation results and other pertinent data built into the model. This data could come from a wide variety of sources and could be incorporated into the Grasshopper model in order to evaluate the merits of a particular design based on interpretation of the simulation results from DIVA. And then the design could be further optimized if it's tied into some sort of optimization algorithm, such as Galapagos, which is inherent which comes with Grasshopper, that can search through the different combinations of variables in the design and arrive at and find the best performing solution. So you kind of have all these interconnections and loops going around. The talk is really going to be in 2 parts. It's going to focus on 2 bodies of work that I've done. One, my thesis from the GSD, which is entitled Facade Optimization Using Parametric Design in Future Climate Scenarios. And the second is going to be a series of ongoing work, actually, for a current project that we're doing at BE using these work processes. Now, my thesis studied ways of optimizing a facade for energy performance, and at the same time kind of questioned this notion of optimization in the context of 1, changing climate conditions, and 2, having different ways of defining what an optimized solution is in the first place. Now, mechanical system energy in a building is a function of providing heating or cooling to deal with loads imposed by heat flows within a space. So you have internal loads coming from people, from equipment, from lighting. You'll have heat losses through infiltration or mechanical ventilation or natural ventilation. You're going to have external heat loads from solar gains, and you're going to have heat transmission through the facade based on the glazing or the insulation in the walls and the temperature differences. So basically, what happens with all those interactions, whether you have excess of heat, requires cooling to compensate, or a deficit of heat, and that requires heating. So some of the design decisions that we make architecturally involve trade-offs. For example, if you increase the window size because you want better daylighting, that's going to help you because now you don't have to use your lights as much. So that saves energy. And then also compensating for the waste heat of those lights is no longer needed. So that enhances the savings in terms of the cooling energy. However, the downside is that your windows are never going to be as insulating as a solid wall assembly. So you're going to have more heat transfer for the facade. So kind of thinking about how to balance all of these concerns and find the optimum solution for your building is really what we're looking for. And you could also think about optimization in terms of a sun shading device, not just a whole building or a whole space, but also building elements. You want to take advantage of the sun in the winter when it might provide some beneficial heat gains for you, but you want to cut it out when you're in cooling season because that'll just impose some additional loads that you have to compensate for. And you do that by looking at when your cooling season is, try to find where your sun angle is going to be at those times. The problem then becomes what happens if there are changes to the circumstances that you've optimized for. Here's a plot of the heating and cooling degree hours for Boston, and using the current TMY weather data. Now, using a climate file morpher developed by the University of Southampton, we could take a look at potential future climate scenarios based on climate models developed by the Intergovernmental Panel on Climate Change. And so it takes that weather file, it morphs it, and here we're looking at the heating and cooling degree days for the year 2020. And you can see, we have less heating required, more cooling required, and your heating and cooling season, your cooling season expands a little bit. That's the area where those lines cross. And then looking further out to 2050, that's the projected climate, and then 2080. So if you've optimized your building to deal with the current condition, you might find that heat balance is kind of thrown off under future scenarios. Or if you optimize a shading device for a particular season under the current scenario, you might find over time that it's less and less effective because your cooling season gets longer. So for the purposes of my thesis, I studied 3 different climates. I looked at Boston, Fairbanks, Alaska, and Phoenix, Arizona, to try to look at different types of climates and how this might apply in different cases. So, and the plots here are the heating and cooling degree hours for those 4 time periods: the current weather data, 2020, 2050, and 2080. And you can see the effects over time. Boston gets more temperate. Fairbanks gets less cold, very cold, and Phoenix just gets hotter. So with Boston and Fairbanks, you see a net decrease in energy use, but Phoenix, you see a net increase in energy use because of the vastly increased cooling demand. So for my thesis study, what I did is I took 4 zones of a typical office building, one facing each of the cardinal directions, and I looked at 3 variables in the facade. Basically, the level of insulation, the window-to-wall ratio, and the length of shading of an overhead shading device for all the orientations. And what I did is, using the Viper component in Diva, I simulated the energy use using the current weather data and then also the future weather data to try to find the optimized solution for each of those scenarios. And then I also did once, that simulation was on a 10-year basis to find the most optimum for a 10-year payback. And then what I did is I looked at a scenario that was a 70-year optimization that incorporated all 4 of the different climate files. And so it would simulate the energy 4 times and linearly interpolate the energy use between those times for each of the intervening years. This is kind of what the process looked like. This isn't exactly my model for the thesis. It's a different model, but it gives you an idea of using Galapagos to run through a bunch of different options very quickly, and with the shading devices and windows, and find the solution that looked at was the optimal. The problem was that I couldn't look at optimal in terms of just lowest energy use, because that would cause the optimization algorithm just to pick the most conservative solution. It would just add insulation, the most amount of insulation in the range that I provided, because it was technically the best energy performance. And we know with insulation that you kind of have this law of diminishing returns, where the more layers of insulation that you provide, you get less and less of an energy benefit. So to try to find that point, we needed to look at different types of metrics. So I looked at two. Basically, I optimized for cost, which took into account your initial investment costs and what you're paying to the facade to construct that facade, and then your energy use for the study period, either 10 or 70 years. And then I looked at carbon, basically the embedded carbon in the materials of the facade construction, and then the carbon use of energy over time. That would give a little bit of a back and forth. So here's just to further clarify a conceptual model of my cost model. So basically what it did is I had these three variables that Galapagos would play with: the insulation, the window-to-wall ratio, and the shading. And Grasshopper would take takeoffs basically from the facade and quantify the materials used in that construction. And then I inputted data from RS means on the unit material prices, installed cost, and that would basically compute for that combination of variables the first cost for that building construction. Then the model was sent to Viper, which performed the energy plus simulation, and I had one of the four weather files set up so that it would simulate that energy use. In the case of the 70-year optimization, it, as I said, did all four. And that would give us the annual energy usage. So then how did we determine period energy cost? We took the 2010 base energy rates from the Energy Information Administration, and then looked at studies that predicted future energy price increases, which went up to 2050. Then we kind of extrapolated them to the whole study period. Basically, for any period that we were looking at, it took the appropriate energy rates and multiply that by the energy use to give us, for this period we were studying, the total energy costs. And that gave us the total cost, which Galapagos seek to minimize. So the carbon model worked much in the same way. The only difference is that with those takeoffs, the embedded carbon on the materials was computed using the University of Bath's database for embedded energy in materials, embedded carbon, and that gave us for the construction. And then an output of Viper was actually the carbon emissions based on the state lookup, and that gave us the carbon emissions from energy use for that period, which gave us a total carbon. Again, Galapagos sought to minimize that amount. So the results that I have here are long and varied, but basically there's some, because there were so many different scenarios. But some of the general conclusions were that the optimized solution does in fact change over the course of time as the climate changes. And within each of the study years, the cost and carbon recommendations were often different. You can see the cost based on this row and the top row, and the carbon based on the bottom. And it seemed that the cost-based optimizations changed more rapidly than the carbon ones. The carbon-based scenarios were more stable, but the cost-based, as energy prices went up over time, they're relatively cheap now, it was recommending more conservative solutions from an energy point of view, despite the fact that in two of the climates, the actual total energy use was going down. It was just that the energy was more expensive. And one thing but you did see the effect of the climate change on the carbon-based optimizations, because it was mostly evident in the shading devices. The shading devices would get longer because it was reflecting that extended shading period that was required. The cost-based optimizations didn't really like using them so much, except on the long-term optimizations, because they just didn't pay themselves back within the 10-year period. But one thing that the model does not include is the reduction, maybe you're downsizing of mechanical equipment due to peak load reduction, which would be interesting to see if, for further study, if that would affect the results. So what these charts represent are this theoretically optimized model for each of the 4 time periods, the energy performance of each of those designs. It would never exist in practical reality because you wouldn't be rebuilding the facade each time, unless it's a really bad facade. But this gives us a baseline to see, okay, what is the energy use for an optimized model, an optimized design in each period. So that's our theoretical baseline. And we see that if we optimize only using current weather data, that this design is no longer optimized over time. It performs less and less well than this theoretical baseline. But if we have a design that's kind of, even on the cost base, if we're optimizing it over the long period, then we arrive at a facade design that's consistently better than if we just optimized for current data, or even for each of the shorter periods. So from this thesis study, there were a couple of general conclusions that were able to come out of it. Namely, that if you're going to only optimize for one point in time, you risk it not performing so well in the long run, because those conditions are going to change. And when you start that process of optimization, the outcome is going to vary greatly based on the criteria that you're optimizing for. So, as professionals that are advising the design team, or part of the design team, there's got to be a decision about what is that optimized result mean to us? What are we optimizing for? What is the value? Is it cost? Is it carbon? Is it something else? And once we've decided that, how do we deal in the design with the fact that the optimized solution is going to change over time? Do we build in flexibility? Do we build in robustness? And perhaps one of the ways to build in that robustness is to take into account the multiple scenarios that might happen, because the numbers that we used were one climate model. What if climate change happens a different way? And the energy price increases was also a different set of models that we kind of averaged together to give kind of a middle of the road, hedging our bets kind of result. If we create this robust design, it's going to perform well under a variety of environmental conditions, even if it isn't necessarily this elusive optimized design. So changing gears a bit, I'd like to talk about some work that's going on right now in our office. This is a massing model similar to 3 such massing models that we got from the architect, the design team at it's a very early stage of development, and they wanted to set, as we're starting off the process, look at the 3 schemes and provide some sort of relative environmental performance for the 3 massings, and see which direction was going to be most conducive to them to pursue. I couldn't actually show the 3 actual models because it's an embassy building and it's also a very secure project. So I kind of made a fourth one up just to show our workflow. And part of the goals of the project were to provide as much of the building's energy as possible through renewables, and to provide a very nice daylight environment. So those were the aspects that we looked at. And we had to really look at PVs in terms of the renewables, because the wind was really so poor at the site, and because of the high elevation of the building, the altitude of the site, we were getting some pretty good solar radiation, so PV was a clear winner. But the idea was, well, how do we strategize where to put the PV? How do we look at the effects of contextual overshadowing of the panels, especially with potential growth happening on sites next door? And how do we deal with shading of the building itself, from the building itself? Because we have all these different roof surfaces. And I guess the next thing to also look at is glare from the PV panels, as we saw in an earlier presentation. But what we did here is we created this grasshopper model that was able to populate all the roof surfaces with PV modules that was able to account for the panel size, the tilt of the module, how we would aggregate these modules into larger arrays and spacing between the arrays. And we ran annual radiation calculation. And then we were able to input into the model a way of interpreting all that, the results of the solar radiation based on a series of derating factors for module efficiency, inverter efficiency, framing factors, and all those things to give us, at the end, an estimation of how much energy over the course of a year a panel is going to produce. And therefore, you can see which areas, some of it is intuitive. You don't want to put panels too close to the building because it's going to be in shadow most of the time, but at least it gave us a way of kind of quantifying it. And then we were able to kind of take it a little bit further, and automatically, if we knew the overall building energy use, and we say we wanted a certain percentage to be generated through PVs, we were able to create in Grasshopper a way of saying, okay, for a given percentage, pick the most effective producing module, start with that, pick the next, keep on going to the next most effective module until you arrive at the result. And this was a way of kind of optimizing the placement. And you could go back and forth and dial it back and see until you arrive at a good solution that's going to be pleasing to the design team, to the client. And that was one thing we did with the PV. The second thing we did is, since it was an early design phase and things kept on evolving very quickly, we had 3 different schemes. We had updates to those schemes. So we wanted to provide a relative assessment for daylighting, but also be able to respond to those design changes and input the new models very quickly. So we created a definition in Grasshopper that kind of took that massing model, carved it up into all sorts of surfaces to create a daylight model. We had interior surfaces, floors, ceiling heights. We could specify window-to-wall ratio. And these were all parameters we could play with to kind of advise the design team as to the best window-to-wall ratio for daylighting. And we could display the results very quickly by importing the results into Grasshopper to a mesh and kind of exploding a little bit and looking at the different results. And even though this wasn't really realistic, because as the design would progress, we would get interior partitions and core functions that would affect the way daylight behaves in the building. At least it gave us the ability to give to the design team some preliminary feedback based on some sort of relative assessment between the 3 schemes, and some idea of window-to-roll ratio. And we could say, well, here I think the depth of your floor plate is too deep, we need to look at something shallower, where to put program as well. Like maybe it's not so bad that you have blue in some areas. You could maybe put your mechanical rooms there, or your core elements. So to strategize the placement of the interior, which was a back and forth scenario with the mask. Now, these last few slides that I'm going to show are really new. In fact, they're from Friday, because we've just moved into the schematic design phase. We're taking a closer look at daylighting and the treatment of that facade. So we're looking at a model of a bay of a typical open office plan in the building. And we want to be able to advise on the window size. And we have some security concerns of this building. There's got to be a certain blast resistance in the facade, which means usually multiple layers of glass. And so increasing the window size for daylight is not necessarily an effective solution, because once you go above a certain width, then you need an extra layer of glass to provide the structural strength. And so the reduction in visual light transmittance might negate some of the benefit that you get from making the window bigger. So that was an interesting problem to study. And then there was additionally, the architect came up with the concept of using a screen that would be a perforated concrete screen that would permit views, but at the same time prevent glare and cut down on some of the direct solar gain to minimize cooling, to minimize overlit areas, and to diffuse light. So the back side of the screen would be kind of angled, so that it would bounce light between the facade and the screen and into the space as more pleasant diffuse light. And so we built this parametric model that allowed us to look at some of the different variables, which was the distance of the screen from the facade, how the surface on the back is angled, how the size of the windows, of the openings in the screen rather relative to the windows, the placement, because we wanted to cut out some of the glare but permit views. So all those could be controlled, and there are a lot of variables in there. So our hope is to study a few different options and then kind of narrow down a selection and use some of the tools at our disposal to look at the cost implications of the screen, of the window size, and of the performance, and build that into the model. And so as we speak, these are all kind of simulating in our office, but I did, before I left on Friday, manage to snag some preliminary results. This is a study of the open office area on one of the facades without a screen. And this metric that I'm using is daylight availability, which kind of combines daylight autonomy and the useful daylight illumination. And what it says is, it looks at the percentage of daylight, percentage of the year that a particular sensor node has daylight above a certain level. In this case, we specified 500 lux. And but the daylight availability part of it is that it subtracts when it's overlit, when it's above 2,000 lux. So you can see here our perimeter zone, the zone that's closest to the facade, is rather overlit. So what this is producing is a daylight availability of 21% of the space. It's kind of a deep space. So in other areas it might be better, but you see, like along the facade, we have a problem. So this was just, one option for the screen. It hasn't been optimized at all. That process is happening now. Looking at one screen, we see that the daylight doesn't penetrate as deeply into the space. But on the other hand, it's making that facade, the area near the facade, more useful. And so we've seen an increase in the daylight availability to 27%, which is a 30% increase, which is good, and it shows that this scheme has some merit. And now, if we kind of play with the different factors, the different variables, we might be able to find an even better solution. So, I mean, that's basically what we are working on now, and I'm really looking forward to see how we can really go further with this study based on the integration of DIVA and Grasshopper and all these parametric tools, and see where it takes us to acknowledge and deal with all the different design concerns that are happening. So thank you.
Thank you, Elliot. Are there questions? Oh, yep.
On your thesis project at the GSP, I guess I'm a little curious why you didn't just map the search space since there were so few variables. I mean, was it necessary to couple this with Galapagos rather than just trying the variations and getting the perfect knowledge of the search space?
I'm sorry, could you repeat the beginning part of your question? What was the other alternative?
Mapping the search space, just trying all of the alternatives, since you only had a fairly small variable set.
So there were only 3 variables, but there were a lot of different options within those ranges. So I think that was part of it. So even though there were only 3 variables, you might have, hundreds of different combinations of those 3 variables. So that's why that's why I did it that way. A lot of it was also an automation of the process. Yeah, that was the reasoning behind the methodology.
So I was wondering about the thesis project. What was actually the goal of the project as such? Because a couple of my observations are, I think you looked at 80-year period, and in 80 years probably the building might be renovated at least once, so 40 and 40 maybe. So that was first observation. The second was when you looked at the window to wall area ratios and say that those were, I think, at this point in time, looking at contemporary design, the solutions look almost impractical. And
they look what?
Impractical.
Okay.
Very few architects today will go with 20%, 10%, I think not 20% window to wall area ratio. And especially in the design process, usually the starting points or the goals are quite different than just looking at energy cost or just looking at so I'll keep it short. I try. But it's usually when you end up comparing energy cost and say cost of your payment to employees, energy cost doesn't even figure into anybody's calculations. So basically, what was the reason for this main goal?
So the main goal was really to look at this notion of optimization. There's a lot of talk about finding the optimized solution, and the thesis was really kind of questioning that to an extent. Like, can you really find an optimized solution? Because you're going to be dealing with changing circumstances. So, I mean, the end results might not be practical, but to say like, okay, if you conceptualize it in a certain way, this is your optimized result. If you look at it a different way, you have a different optimized result. So how can you not necessarily optimize, but find a good solution that's able to deal with different scenarios or achieves the goals that you are looking to achieve by incorporating all this outside data into the process and kind of taking into account. And if someone says, well, I want a 10-year payback, well, what type of energy conservation measures are going to be in the solution in the 10-year payback, because it's going to reduce the energy cost enough. But if you do that, are you too short-sighted because over time they're not as effective? So that was kind of the main thrust of what I was trying to look at.
Maybe just as an add-on to that, I think the thesis was also supposed to be a joke. And I mean that in the best of all senses, because usually actually when we were to kite, we also put some of the SOM black box group pictures there where you sometimes see radiation maps and there's this notion of the building has to look that way because it's climate responsive. And when you look at that, it's more, well, the climate changes, it's to say that be upfront when you make a design decision and don't always try to hide between the climate, because the climate change has bigger implications than actually the width of your overhang. So the joke was in there somehow, that we questioned ourselves.
I think just in response to that too, I mean, it is interesting that, how much do people value energy or whatever. It seems like that would be easy to solve if you asked the client for their discount rate and then used the net present value and said, okay, well, if you invested this money elsewhere, what would be your return? So let's put it into context of all the investment options. So I think it can still work in there somehow.
The reason I asked about the goal was because a lot of times thesis goals are quite different than the conclusions, in the sense that you're looking at a very specific thing and you might end up with different conclusions. But what did you start with?